Humans leverage constraints to perform complex tasks. However, some constraints depend on temporal conditions. For example, in the shallow hole insertion task, humans initially contact the peg to the hole, which is a subgoal, and after keep stable contact until the insertion, as a local constraint. To address such temporally dependent behaviors, we propose ILCL, which learns temporal logic constraints from demonstrations. ILCL follows two-player game framework that learns constraint by an adversarial optimization between a constraint player and a policy player. We extend this framework to learn truncated linear temporal logic constraints from temporally constrained demonstrations. The constraint player GATL mining uses a tree-based genetic algorithm to search for the best constraint in the form of an abstract syntax tree. The goal is to find a constraint that penalizes generated trajectories while labeling demonstrations as safe. The policy player, Logic-CRL, performs constrained reinforcement learning using the constraint output by GATL mining. To handle the trajectory-level binary logic constraint, we apply constraint redistribution to obtain stepwise continuous logic costs. After the iteration of this two-player optimization, we select the constraint that best recovers the demonstrated behavior. We then use Logic-CRL to transfer the learned constraint and train new policies in unseen environments. We evaluate our method in simulated environments. For instance, in the peg-in shallow hole task, which requires a sequential insertion strategy, ILCL successfully learns the underlying temporal constraint and transfers a demonstration-like policy to unseen settings. We also test ILCL across a variety of environments with temporally constrained demonstrations, and show that the learned constraint transfers successfully. We conduct real-world experiments to assess whether the learned logic constraints can induce complex manipulation skills. We apply Logic-CRL in the real world to transfer constraints learned in simulation. To minimize human effort, we design a custom reset device. After 2.5 hours of training, we obtain a constrained insertion policy that closely resembles the expert demonstration. Finally, we test the robustness of the learned constraint by varying the insertion angle of the hole. These results highlight that learning well-structured temporal constraints enables agents to acquire complex manipulation policies.